Hello, Algebra 2 students. This video is going to go through and go over the notes for graphs of exponential functions. So if we were to be in class, we kind of have a little intro, but since we aren't, we're just going to jump right in. So I got two quick kind of questions here before we start with what is an exponential function. So the very first question says, is y equals x to the fifth an exponential function? And this is not an exponential function. And the reason why is really because it is a polynomial function. So we talked a lot about polynomial functions back in maybe like January and February, but polynomial functions really had to do where you had x to some whole number positive power. So like for instance here, we have x to the fifth power. So that was what we called a quintic polynomial. So this is not an exponential function. If we look at the second question though, very similar to the first one, it says, is y equals 5 to the x an exponential function? And the answer is yes. And the big difference is here, notice we have some base, in this case 5, but notice your variable, so if I kind of write this here, your variable x happens to be in the power. So I'm just going to put here yes, and then when the variable, which is most notably x, is in the exponent. So that's kind of a quick starter. We'll talk more about exponential functions here in a minute. So we're going to get off to an example. And the first example says here, graph f of x equals 2 to the x. Now, if we don't know what a function looks like, for instance, like a quadratic or a polynomial, ones that we've done earlier in the year, the easiest way for us to kind of graph something is to create a quick XY table. So if I stick close to 0, so maybe like -3 all the way to +3, we're just going to think about plugging these values in for x. So for instance, here we'd have 2 to the power of -3 because I'm plugging -3 in for x. If we kind of review back a couple weeks, we know that negative exponents move things down to the denominator. So this would be like 1 over 2 cubed, which would simplify to 1/8. So we could plot this point -3 and we'd have to approximate, but maybe right about there is 1/8. And then we could do the same thing here. We could plug in -2 and you're going to get here 2 to the -2nd, which simplifies to 1/4. And we could go ahead and maybe approximate, maybe there's 1/4, and we could plug in -1 for x, and we're going to get 1/2. So we could plot the point here. Again, we're approximating. There looks about negative, say 1/2. If we plug 0 in, remember anything to the 0 power, because we're going to have here 2 to the 0, well, that's 1. So then here we could go ahead and plot 0, 1, and then we can just keep going. So if we plug 1 in, we're going to get 2. So if we plot that, if we plug 2 in, we're going to get 4. So if I go ahead and I plot that, and if we plug 3 in, we're going to get 8, because 2 times 2 times 2 gives us 8. We get point there. So then if we go ahead and connect these dots, we'll notice that we kind of get a nice graph here that quickly rises as we go from the left side of our graph over to the right. So you might have heard people talk about exponential growth. All right, so this would be an example of exponential growth, because if I look at each one of these, for instance, this y value is 2, and then this y value is 4, and then this y value is 8, every time my y values are multiplying by a factor of 2. That's my base. So this would be an example of exponential growth. We're doubling each successive x value. So if we go ahead and we look at this really quick, we're going to talk about some graphical analysis that we've done throughout the course of the year. We're going to start here with domain. Domain, remember, is our x values. So if we think about the graph going to the left forever and to the right forever, well, then our domain here is going to be -infinity to infinity. Now we're going to talk about range. So range is y values. So if we think about our lowest y value to our greatest y value, we can see as we go to the right, our y values, we can kind of see here, are going up forever. As we go to the left, we notice that our y values get smaller and smaller. The question is, will they ever become negative? And to answer that question, we're going to kind of go back up here to our equation. We're going to say, can we ever plug in a value for x meaning can we ever take 2 to a power that's going to give us a negative value, right? So if we think about taking 2 to maybe a negative power, well, remember negative exponents, like we kind of saw here, are just going to kind of take the reciprocal of the fraction, but they're not going to make it negative. So actually what we end up with here, right along the y-axis, x-axis, is we end up here with an asymptote at y equals 0. So we could say, okay, here, actually the third thing down, we could say, well, look, we have an asymptote there at y equals 0. It's never going to give me a negative value no matter what I put in for that exponent, which means then that our range, our lowest y value is going to be 0, and we already said as we go to the right, it's going up forever. It keeps getting higher and higher and higher, so it's going up to infinity. All right, next we can look at increasing. Remember, we've talked about increasing is where our graph is going up from left to right, or has this notion of positive slope, which if I look at my graph, it's increasing. It's going up the entire time as I go left to right. So I'm going to say negative infinity to infinity. My graph is always going up, which means that where it's decreasing is it's never. So I'm just going to put none. It's never decreasing. If we talk about end behavior, we've done this a couple times where we write x, arrow, negative infinity, y, arrow. So as our x's go towards the left, our y's are going towards 0. If we do the same thing as x's go towards positive infinity, y's go towards, positive infinity because we're going up forever. All right, so there's a quick kind of example of a exponential function. We're going to do a couple more, but before we do another one, I want to kind of maybe review the basics of what is an exponential function. So I have here in red at the top a definition that really says an exponential function has a standard form of this, and if I go ahead and underline it over here, y equals a times b to the x. And these a and b values really represent numbers. The a value is what we call the initial value. And this initial value is really, okay, what does your function equal when x equals 0? That's your initial value. Your b value is what we call either the growth or decay rate. So it's kind of how fast your function or your exponential is either going up or going down. So if we kind of expand on this a little bit, the first example we saw was an example of a growth function, right? It kind of looked something like this. So I'm going to go ahead and put here growth exponential. All right, and a growth exponential is any time where we have this b value greater than 1. So anytime your b value, that value being raised to the exponent of x, has a value greater than 1, that's going to be a growth. On the other end of the spectrum, we could have a decay function, which looks something like that. So if I go ahead and write here decay exponential, well, a decay exponential is going to have a b value somewhere between 0 and 1. So you might think of this as like a decimal between 0 and 1, or maybe a fraction between 0 and 1. So those are our two types of exponential functions. Now, just like we've done before, we did it with quadratics, we did it with polynomials, is we can kind of have transformations on these graphs that can move them left or right or up or down. So I got 3 questions here, and it says, what does v, so what does the variable v, do if y equals a times b to the x plus v? So if you want to pause it and think about it for a minute, you can. But your v value is going to be your vertical shift. So it's going to move your graph up and down depending on what that v value is. If you add a value, it's going to move my graph up, which means it moves that asymptote that was on our x-axis, it's going to move it up. If that v value, say, is minus some number, then that's going to move our horizontal asymptote down. Then we may go underneath the x-axis. All right, and if we look at number 2, it says, what does h do? Probably most of you can guess. Well, it's going to be a horizontal shift, right? So if I go ahead and I write horizontal shift here, and we've talked about this before earlier in the year, is it's going to be the opposite as what it appears. So if you notice here, it's y equals a times b now to the power of x minus h. If you're subtracting some value from x, so maybe it's like x minus 3, that's really going to move it to the right 3 units. If you're adding some value, that's going to actually move it to the left that many units. And then if we talk about reflections, we really have a couple or two choices. If we want to reflect over, say, the x-axis. So if we want to reflect over the x-axis, it's going to be y equals a negative, and then you'll have your a times b to the power of x. If we want to reflect over the y-axis, well, we need to make the x value negative, so it'd be y equals a times b to the negative x power. So just to kind of review some of the transformations we've done so far this year. So with that, we're going to do one last example, and it says here graph, and we have y equals 4 times 1/2 to the power of x. So again, I'm going to go ahead and I'm going to make an xy chart or table. I'm going to start here maybe -2, -1, 0, 1, and 2. And we're just going to plug these values in. So if I think about plugging in -2, I'm going to have 4 times 1/2 to the -2nd power. Now, remember, order of operations. So I've got to take care of the exponent first. So I think 1/2 to the -2nd power. Well, negative exponents, they go ahead and move things. So we're going to have here 4 times 2 over 1 to the second. Well, 2 over 1 is 2. 2 squared is 4. So we end up with 4 times 4, which is 16. So if we plot -2, 16, we're going to be like maybe somewhere up here. If we plug -1 in, again, make sure you follow order of operations. I believe I get 8. So if I go ahead and I plot -1, 8, maybe I'm right about there. If I plug 0 in, well, 4 times 1/2 to the 0 power. Anything to the 0 is 1, so 4 times 1 is 4. So that goes and tells me I have a point there at 0, 4, which hopefully we talked about this value out in front. That's our a value. That's your initial value. When x equals 0, this is telling you your initial value. It's also telling you that y-intercept. So just another quick little hint that's telling you that y-intercept. If we keep going and we plug in 1 for x, we're going to get 2. And if we plug 2 in for x, we're going to get 1. So if we plot those points, looks like here, looks like here, you should see, well, our graph has kind of got this nice kind of even decay to it, or this kind of nice slope downwards to it. I'm sure yours will be much cleaner than mine, but it should look something like this. If I make my points a little bit darker here, looks something like that. And then we can even look at this and we can say, okay, well, look, for instance, here we had a y value of 8. Here we had a y value of 4. Here we had a y value of 2, so on and so forth. But that y value is really telling you how it's decreasing as we're decreasing by a multiple of 1/2 every single time. So, quick intro into exponential functions. There is a video in Schoology that I would recommend because as we get deeper into exponential functions, we're going to start talking about a number that's called Euler's constant. And Euler's constant is a lot like pi. So back in geometry, we learned about this number pi, which is 3.14, and it kind of keeps going forever and ever and ever. A number that comes up with these exponential functions and exponential growth and decay is a number that we call E, or Euler's constant, that is approximately, so maybe make that a little approximation, and it's approximately 2.718, and it continues on and on forever. But again, like I said, there's a good video in Schoology. I recommend you watch it. Kind of talks a little bit more about this E value and where it comes from. So that's it for these notes. I will see you later.